In the last lecture, we got introduced to Euler-Lagrange equation of motion, which was d by dt of del L upon del Qi dot minus del L upon del Qi is equal to 0. In this lecture, let's explore further. We know that del L upon del Qi dot is equal to generalized momentum, which is Pi. So if you substitute this in Euler-Lagrange equation of motion, we get d by dt of Pi is equal to del L upon del Qi. Now you can represent the total time derivative by a dot. Therefore we can write Pi dot is equal to del L upon del Qi. This relation may come in handy to solve some problems, so take a note of it. Now again come back to Euler-Lagrange equation of motion. In this equation, if you put L is equal to t minus v, you get d by dt of del by del Qi dot t minus v minus del by del Qi of t minus v is equal to 0. From here you can write d by dt of del t upon del Qi dot minus del t upon del Qi is equal to d by dt of del v upon del Qi dot minus del v upon del Qi. This thing in the right hand side, it is called generalized force and it is denoted by capital Qi. So capital Qi is equal to d by dt of del v upon del Qi dot minus del v upon del Qi. This is generalized force. In the Newtonian mechanics, force is F is equal to minus gradient of potential. In one dimension, Fx is equal to minus del v upon del x. And generalized force we obtained here is Qi is equal to d by dt of del v upon del Qi dot minus del v upon del Qi. For conservative systems, where potential is a function of Qi only, del v upon del Qi dot will become 0, and this implies Qi is equal to minus del v upon del Qi. So when the system is conservative, when v is not depending on Q dot, then the force, the generalized force, become equivalent to the force in Newtonian mechanics. The force in Newtonian mechanics is Fx is equal to minus del v upon del x. So from here we obtain another form of Euler-Lagrange equation, which is another form of Euler-Lagrange equation. d by dt of del t upon del qi dot minus del t upon del qi is equal to qi. This is another form of Euler-Lagrange equation and is particularly useful when potential is unknown. When we don't know the potential, we can use this form of Euler-Lagrange equation to find the dynamics of the system. Now there is one more form in which you can write Euler-Lagrange equation, which is called Nielsen form of Euler-Lagrange equation. The derivation is not important, so I am skipping that, but you have to remember this: del t dot upon del qj dot minus 2 into del t upon del qj is equal to qj. Now let us move on to Hamiltonian. Hamiltonian is a function of generalized coordinate, generalized momentum, and it can be a function of time as well. In Hamiltonian formulation, qi and pi are assumed to be independent of each other. The Hamiltonian is obtained from the Lagrangian through Legendre transformation, and it is written as H is equal to summation over I pi qi dot minus L. If L does not depend explicitly on time, then H is called energy function. H is called energy function if del L upon del T is equal to 0. That is, Lagrangian is not explicitly depending on time. If you take the partial derivative of H, of the H here, you will get, if you take partial derivative of H with respect to time, you will get del H upon del T is equal to minus del L upon del T. Now let us move on to solve a problem from NET December 2024. Here we have a pendulum, and the pendulum is connected to the roof of a taxi, and the taxi is moving with a uniform velocity v. We have to find out the Lagrangian for the pendulum. For a pendulum with the point of suspension in rest, x coordinate is given by L sin theta, and y coordinate is given by minus L cos theta. But here we have point of suspension which is moving with velocity v, because the taxi is moving with velocity v. Since the taxi is not accelerating, we do not have to consider fictitious forces. It is only moving with the uniform velocity. So after some time the pendulum reaches here. After time t, the point of suspension moves a distance which is equal to vt. Therefore the x coordinate of the pendulum is no longer L sin theta itself, but we have to add Vt as well. L sin theta is due to the oscillation of simple pendulum and Vt is due to the traveling of the taxi. Now we know the x and y coordinate. There is no change in y coordinate because there is no motion in vertical direction. We can write now the kinetic energy. T is equal to half m x dot square plus y dot square, and V is equal to, we have to put x dot and y dot here. V is equal to mg y, which is equal to minus mg L cos theta. And Lagrangian is equal to T minus V in almost all cases. Rarely Lagrangian is not equal to T minus V. T is equal to half m x dot square. X dot is equal to, x is L sin theta plus Vt. So x dot is equal to L cos theta theta dot plus V. Y dot is equal to, y is equal to L cos theta minus L cos theta. Y dot is equal to L sin theta theta dot. Therefore kinetic energy is half m x dot square is L square cos square theta theta dot square plus V square plus 2 L V cos theta theta dot. This is x dot square plus y dot square is L square sin square theta theta dot square. This is the kinetic energy minus V. V is minus mgl cos theta. Therefore this will become plus mgl cos theta. Now we can use cos square theta plus sin square theta is equal to 1. L is equal to 1 by 2 m L square theta dot square. Cos square theta plus sin square theta is 1 plus V square plus 2 LV cos theta theta dot plus mgl cos theta. This is equal to half m L square theta dot square plus half mv square plus mlv cos theta theta dot plus mgl cos theta. Therefore the correct option here is option 1. L is equal to half m L square theta dot square plus half mv square plus mlv cos theta theta dot. No, this is incorrect. Option 2 is correct answer. Here it is plus. So L is equal to half m L square theta dot square plus half mv square plus mlv cos theta theta dot plus mgl cos theta. Because when we minus v, it will become plus mgl cos theta. Now, is the Lagrangian that we found here is unique or not? No, it is not unique. Because if we change the potential energy zero level, then the Lagrangian will also change. In this problem, we assumed potential energy equal to 0 at the point of suspension level, right? At y equal to 0, we chose potential energy equal to 0. Some other person can choose the potential energy equal to 0 at some other level, then the Lagrangian will also change. But convention is to choose the potential energy 0 level at the point of suspension. I hope you understood today's discussion. If there is any doubt, you can put it in the comment section. If this is helpful, you can share it to your friends. That's all. Thank you for watching.